Okay, for number 6, we have a radical. So this is composition of radicals. So with a quadratic. So determine the domain of J and K. So you guys know how to do that, and go ahead and try that. We're going to try this maybe as a class work. I know this, the domain of the composition will be a little bit tricky. So I'll help you with that. It's more this one. B is tricky. So determine the domain of J and K, then see if you can figure out J of K of T just by plugging in. That one's not algebraically challenging. Let's try not to do too much with it, more than you want to do. And the same thing here. I think it's just the domains that are tricky. So go ahead and work those out and check back. I'll go through them really quickly, and then we'll talk about the domain. Okay, so the domains on these for J would be T is greater than or equal to 1, and for K, it's all real numbers. It's quadratic, so hopefully you're getting used to those kind of things. For J of K of T, so we're just going to take K of T here, T squared minus 5, and plop it in everywhere we see T. So that one time, so it goes right in the for T under the radical. And then we have minus 5, so T squared minus 5 minus 5. So we can just simplify this pretty, I don't know why I wrote a 5 there. It should be 1. Let's look at the other one. So it's T minus 1 is my radicand, so. And then I have simplification on that. So I would have J of K of T equal to radical T squared minus 6. So again, the square is only attached to that T inside the parentheses, so we're good to go there. So that's my answer for that. Looking at what the domain is, though, is a little trickier. We need to think about what's the domain of our inner function is just all real numbers, so we have no restrictions there. But we need to know when T squared is, or T squared minus 6 is greater than or equal to 0. And there's a couple of different ways you could do that. I think graphing is pretty easy. You can figure out the zeros for that by just using the square root method here. So we could do T squared greater than or equal to 6, and then take the square root of both sides. So we get T is greater than or equal to plus or minus square root of 6. And then do a quick sketch of a graph. We could plot these, let's see, -6, square root of 6 zeros right about there, negative or positive 1 is there. And we know it's opens up. So our parabola will be kind of like this shape. So where this parabola is positive, and those segments there. So it would be, this is negative square root of 6, 0. This is positive root 6, 0. So my domain is going to be negative infinity up to negative square root of 6. Just using interval notation for this one. You could do it as greater than or equal as well. And that would be union. And then we could also have it as square root of 6 to positive infinity. So that would be my answers for part B. And that gives me the domain of my composition, the domain, don't forget, of your inner function. That was already real number, so we didn't have any restrictions there. Let's look at k of j of t and determine its domain. So k, now we're going the other way here. So we have radical t minus 1 being plopped in for t in the k function. So k of j of t will be, our outer one is the t squared, so we're going to have parentheses squared minus 5. That's another way you could do it. And then pop that j of t in there, which is square root t minus 1. And then we're going to take the square of a radical. So we just end up with the radical, or the radicand. It's inside there, and then minus 5. So we get t minus 6. And we need to check the domain. So this is our composition. Our inner function, j of t, the restriction was that it had to be greater than or equal to 1. Or you can write it in interval. Let's stick with interval because that's what we started with on the other one. We also have to check our composition, but there's no restrictions there. We're good for that. No restrictions on composition. So what I find the common mistake is people forget to check the inner restrictions, the inner function restrictions. They just do like the outer, or they might do the inner and the outer, not the composition. Again, you could do it the longer way. You could set the inner function equal to be not equal to the restriction on the outer function, if you want to do it that way too. But it gets all taken care of in the end there. So that is our answer for that one. That went pretty quick, so I'm going to get this word problem done as well. A patient is given an injection of a therapeutic drug that has a side effect of raising their heart rate. The patient's heart rate in beats per minute is given by Q equals 60 plus 0.2 Q, where Q is the amount of the drug in the bloodstream in milligrams. Over time, the body metabolizes the drug and the level of the drug in the bloodstream falls accordingly. The quantity of the drug in the bloodstream is given by Q of T equals 500 divided by quantity T squared plus 2, where T is the number of hours since the injection was given. So our key things we want to just outline here, we have Q, and that's going to be our amount of drug in the bloodstream. And then we have, that should say H of Q. Let's fix that. So it should be H of Q. Sorry about that. So H of Q. And then we have Q of T, which is the quantity since the injection was given, and it decreases with time passing. Kind of makes sense, right? So we have to think about how quickly is the heart rate increasing or decreasing with respect to the amount of drug. We would have our rate of change. It's going to be our change in the heart rate over our change in the quantity, okay, based on like how the time passes. So we are given in the heart rate that we have 0.2 Q. Okay, so we have 0.2 per 1 milligram. Okay, so that's what this is right here. We're just using the H function right now. So that is our slope, our rate of change. So it's 2 beats per minute per milligram of drug. Okay. Describe what H of Q of T represents. So this is the composite that relates to the heart rate to time. So we kind of have to get the time factor in there, and this is how we're going to do it. So this is our start time, or starting spot. Okay, I should say. It's the time that's passed, okay? And then Q is our amount of drug. And then finally, the outer function is going to be our heart rate in beats per minute. Okay, so this is the time, not our start time, but the time passed. But that's where we're starting inside our function. Okay, and our final output would be the heart rate. So T is our input starting spot. That's going to be the time passed. And then in hours, so we could track that down. And then the heart rate is in beats per minute. Amount of drug is in milligrams. So how much of the drug was injected? So part C, let's take a look at that. So if we want to know that quantity, we need to use the Q of T function. And specifically, we want to know what Q of 0 is, because that's our initial time. So no time has passed. Okay, so that's actually a start time. And we would have 500 over 0 squared plus 2. So that's going to be 250 milligrams. And we want to say at initial injection. Part D. According to this model, what would be the patient's heart rate? What would the patient's heart rate be if the drug was not injected? So then for this one, we want to just look at the H function, right? H of Q, because we have Q. If nothing was injected, that means quantity is 0. So we have H of Q equals 60 plus 0.2 Q. I'm just rewriting this so you can see it clearly. And then we want to find H of 0 when quantity is none, right? So what is their heart rate when they haven't had anything? And that would be 60 plus 0.2 times 0, which would give us 60 beats per minute is their just normal heart rate without injection. It's pretty low. Maybe they're just laying still, right? So now we need to find what was the patient's heart rate after 2 hours after injection. We're going to assume they were injected here. It's kind of not clear. So for that one, see if you can figure out how you would do your composition. I give you a hint up here at B. And so if you can plug stuff in and figure that out, so pause the video. Okay, so now we're going to find H of Q, of T. And we need T equal to 2 hours. But first, let's figure out what that composition is. 500 over T squared plus 2 will equal 60 plus 0.2 times 500 T squared plus 2. That will equal 60 plus 100 over T squared plus 2. So that is my composition. I don't have any restrictions there, it looks like. Of course, we can't have time negative in our original it wouldn't give us we would always be squaring it, but it wouldn't make sense to the word problem to have time be negative. So we would want time greater than or equal to 0. So sometimes it's not going to give us an undefined situation mathematically, but for common sense wise and restriction of like the word problem context, we would want to have a time greater than or equal to 0. We're not putting them back in time. So our T is 2, so we can just go ahead and plug that in. So we can find H of Q of T, or for any T. That's why we want to figure out these formulas. So I'm going to put 2 in there. And we would end up with 60 plus 100 over 2 squared would be 4, plus 2 is 6. So we have 100 over 6. And for word problems, we can just use decimals. We're going to round off in that. And so we have 60 plus 16.666667. And so we'll just round 2 places. So our answer would be 76.67. And we're talking about heart rate. So it's beats per minute after 2 hours. Okay. So that's the answer for part E. Continued. Now part F is asking, when will the heart rate be below 70 beats per minute? So we want to set up our H of Q of T, because we need to include time and heart rate. So we have to roll them together. And we want to know when it would be when 70 is greater than all that. So we're going to have, this is one reason we had to have our formula done out, our composition formula. So we're going to set the H of Q of T equal to 70 and then solve it. So I'm just going to kind of replace this just to make it have more room, but that's the same thing here. H of Q of T is now 70. We want to know when our heart rate stuff is going to be less than that. So we would end up just solving this out. 10 is greater than 100 over T squared plus 2. And then we can clear the denominator. Times T squared plus 2 on both sides. And we end up with 10 actually, let's do it this way. We can actually divide both sides by 10 at this point. And we will get t squared plus 2 is greater than the 100 divided by the 10 would be 10. And then we get t squared must be greater than 8. So then we have t is going to be greater than plus or minus square root of 8. And again, we only want positive values. So once we crunch that out, we could find the square root of 8. And that would be, so we're just going to take the positive. I'm going to make a little note. Only want positive. So t is going to be greater than 2.83 hours to keep that below 70 beats per minute. Okay, and usually, write sentences out when you're doing a test and things like that. It can be brief, like this. You just squeeze in heart rate. Okay, so that's our big word problem there. And that's ending this video, and then I'll do the puzzle thing at the end, which is pretty tricky, but if you want to try that one, go ahead. I will let you skip that if you don't want to do that one right now to submit for homework. You can, or for note taking, you can just kind of dabble with that later. I know these are getting pretty lengthy.